engage with you in order to motivate my talk. So I'm going to basically ask you two questions, two different kinds of questions. Number one is that if you are the design team in an organization, and we've been asked to design a system, the group has come up with two alternatives. And the performance measure that we are interested in is the mean time to failure. And the two systems we have simulated, and we have determined that the distribution of the mean time to failure of alternative 1 has a normal distribution with a mean of 100 weeks and a standard deviation of 5 weeks. And the second alternative design has a mean time to failure distribution that is normal, has a mean time to failure expected value of 100 weeks, and a standard deviation of 25 weeks. Now, which system would you select? Those in favor of system alternative 1, raise your hand. How many of you are going to select alternative number 2? So I think by default that the rest of you are alternative number 2. So why are you selecting alternative number 2, which has the two systems, they have the same mean time to failure, 100 weeks. But alternative 1 has a standard deviation of 5 weeks. Alternative 2 has a standard deviation of 25 weeks. Which system is better if our performance metric is mean time to failure? First one, of course. And of course, the reason the first one is because the distribution of the mean time to failure is narrower, skinnier, whereas the other one is flatter or fatter. So therefore, in that case, we have compared the system on the average of the two distributions, but also we have taken another metric into account, and that is variance, the risk associated with it. Now let me give you another example. Let's say that I ask you to engage in a lottery game, and the lottery is this. You are going to get 10 rupees with probability 1, or you are going to get 1 million rupee with probability of 10 to the power minus 5, or you are going to get 0 rupees. Which one are you going to select? How many say first one? Okay, how many would say second? Okay, so, and that is very common. Engineers are, most of the people in the audience are engineers. They take the sure thing, which is 10 rupee, as opposed to something which is very risky. But not everybody, there are some people who are going to take the risky alternative, and it shows that human beings, they process information differently. And if we use the concept of utility theory, we have different utility functions. And those people who are expected value optimizers, they take the sure thing, they have a linear utility function. Whereas the other people, the group who took the second alternative, they do not have a linear utility function. So, we engineers, we have been trained to look at expected value. Most of us, we decide on selecting a system based on expected value. So the talk that I'm going to be giving to you is, I want to impart upon you that if you're an expected value optimizer, you are missing something, and that is not good enough in certain type of situations. In certain situations, it's going to work. But if you are concerned about the risk of performance of the system, expected value is not a very good metric to use on a performance measure of this decision. So the work that we are presenting is with a colleague of mine, Professor Demet Batur, who has started my postdoc and now is an associate professor in our university. So I want to give her a lot of credit. She has carried most of the work in this area. So the outline of presentation is that first I'm going to talk about measures of comparisons and selection of a stochastic system. So, as I mentioned yesterday, most systems that you're interested in, they have some inherited uncertainty. And if you use random variables to model those uncertainties, then you're talking about stochastic systems. So the question is, how do we compare the stochastic systems? So, and I want to break this down into two categories. One is optimization models, and the other are simulation models. And of course, optimization models are the ones that you can come up with a formulation that you can solve. And simulation systems are for complex systems that you need to simulate in order to decide. And then we talk about the simulated system. Primarily, I'm going to be talking about the simulated system selection based on risk-sensitive measures. And three of them I'm going to be talking about. One is the mean variance, example number one, that you took the variance into account by selecting the alternative which had the smaller variance. And of course, in that case, variance is a surrogate for risk. Quantiles, and first order stochastic dominance. And we are going to be talking about the challenges, computational challenges associated with these systems. So let's look at the optimization models. And if you look at optimization models, generally, let's say you're going to minimize a function and subject to a set of constraints. Some of them are equality constraints, some of them are inequality constraints. And then if any parameters of this model are random variable, then the objective function is going to become a random variable. And then therefore, we need to use the stochastic optimization techniques to solve. Now, if you look at the literature on stochastic optimization, the legacy approach is to minimize the expected value of the objective function. And that is the approach that we take. Normally we look at some scenarios, and based on those scenarios, we try to minimize the expected value of the optimization. So let's assume the Z has a distribution which looks something like this graph that I have on the screen. Now, the expected value is shown by E someplace, and then how about the tail? If it's mission critical, do we ignore the tail? As I mentioned, in the example number one, the two systems can have the same mean, but how about the shape of the distribution? Is that something that we need to be concerned about? So, people in finance, they are concerned about the risk, and when they invest, they take that risk into account. And in the field of finance, they have come up with value at risk. And they say, all right, if we are talking about a value beyond that, which is the risky part, we want to basically minimize that. So if you look at the cross-hatched area, what people have used, they say, all right, we are going to be looking at the Z to power Q, which is a quantile value, value at risk, or we are going to look at the expected value of the area which is cross-hatched. Now, in 2000, Rockefeller and Yurisov, they came up with a paper that said, all right, we can show you how to model minimization of the conditional value at risk, which is the area under this graph that I was showing you, the area under the hashed area. So if you want to take that area, in other words, we want to minimize the expected value and minimize the expected value of the cross-hashed area, he provided a method, a technique, gimmick, and he proved in this paper that the result is actually gives the correct answer, the correct way of modeling it. So since then, the idea of taking a risk into a stochastic programming has appeared in the literature. So in a sense, what we are trying to do is either minimize the expected value, ignores the risk, or we can just look at the conditional value at risk, try to minimize that, or we can take the expected value plus a weighted amount of the conditional value at risk. In other words, the trade-off between the risk and the expected value. So in the literature of the optimization, stochastic optimization, really we are talking about three measures. Either we are talking about the expected value of the objective function, the conditional value of the objective function, or a combination of both. So that's on the side of the Now, on the simulated system, I always say to my students that everybody can simulate, but not everybody can simulate correctly. And I think that's the issue. On the simulated system, we need to statistically guarantee the selection of the best system. So if I have two systems I'm going to simulate, how sure am I that the system that I'm selecting is the best system? Okay, so that's really a big challenge. And the other issue that we are interested in is we want to minimize the number of simulation, which is our computation budget. Although nowadays, because of the abundance of computing power, the budget is not as important because we can run the heck out of the model and get the results, but still, some kind of a guarantee that the solution that they've come up with is indeed the best solution is very important. And most of the engineers, and I look at the literature, most of the people who are simulating, they are not thinking that way because they ignore that issue. So now, on simulated system selection measures, again, traditionally everybody uses the expected value, and it's relatively easy to guarantee a statistical validity. And the reason is that because we use central value theorem, we say the underlying population is normal. If the underlying population is normal, we can use, in a sense, a t-test and guarantee that 99%, 95%, the solution that we have come up with, the expected value, is within the bound of errors, and we're good. Okay, so that's easy. Now, if you want to use mean and variance, really the test on the variance side is much more complicated. Because you have to guarantee that you have selected a system, I'm going to be talking about this a little bit more detail later on, that your mean is good and your variance is good, so both of these, and statistically the problem becomes a lot more challenging. And then if you want to use quantile, which is a value at risk, then again, the problem is challenging, it becomes very challenging. So, and the stochastic, first order stochastic dominance, which I'm going to define shortly, is really taking the whole distribution into account. So we are talking about the whole distribution, a point on the distribution, two metrics of distribution, or one metric of distribution. Really, that's what we are talking about. Okay? So now, problem statement number one, that relates to the first kind, is select the best system from K-simulated stochastic system based on the mean and variance dominance. And the definition of the dominance is this: system A has a mean and variance dominance over the system B if system A, expected value of system A is bigger than expected value of system B, assuming more is better. And the variance of the system A is less than the variance of system B, and at least with one inequality. So this is the weak dominance when they have equality. If one of them has to be with inequality in order to have a weak dominance, otherwise you don't have any dominance. All right? And variance in this case is used as a surrogate for this. We have a paper in the Informal Journal of Computing that was published in 2018. We guarantee the probability of the correct selection with whatever value the designer or the system selector is one to use. So basically, our approach is based on a three-way hypothesis test, and we have three-way hypothesis tests on the mean and three-way hypothesis tests on the variance, and on that basis, we are going to decide which one is better. And these are the conditions under which the system 1 is better than system 2, or vice versa, and so forth, and then we can say there's no dominance under the third category. Now, for both mean and variance, we do have from a sampling point of view, which is the simulation budget, we have a continuation space that we keep sampling until we say, all right, we have guaranteed the probability of correct selection vis-a-vis the mean. All right? So if you look at this space that I have, we are going to stay within the lines. As soon as we cross the line, that means we are satisfied. So this is as long as we have not satisfied our condition, the guarantee, we keep sampling. We are in a continuation space. And if you notice, as the number of samples increases, the continuation space becomes narrower, because eventually, because of the law of large numbers, we are going to get out of that space. All right, so as you see, at the beginning, it's fatter and gets skinnier as we move forward. And this is for the mean test, and the details, the mathematics are in the paper. I don't want to bother you, and we do have the proof of the correct selection in the appendices of the paper. But for the variance test, we have the same thing, a continuation space that we keep sampling. And remember, for mean variance dominance, we have to satisfy both. And then we are going to stay with the continuation region until we come up. So what we did in that paper, we presented an algorithm that guarantees, and we have a statistical proof for it, that guarantees correct selection. And the details are there, so again, I don't want to bother you with mathematically. And we applied this to a paper in the field of electrical engineering and the mean variance approach to transmission network planning. Right? So, and the question is, if you want to use mean and variance, and most of the transmission planning models, they want to minimize the cost of energy, and the question is, if you have these systems, transmission alternatives that we can build, which one is the best one? And of course, we want to build the one that is going to minimize the cost of the system. And so basically we approach this. And let me show you the flow chart of this. Again, the details of that is in the paper. And we are going to come up with a model. And we keep solving a deterministic model of the transmission planning. And whether it's AC or DC, you know, that's, you can decide which way you want to do it. And of course, AC is a lot more complicated to solve because it's nonlinear. The space is nonlinear. The physical region is nonlinear. And we do develop a model for the system, and we keep sampling the parameters of the model, which are uncertain. In the case of transmission network, we can talk about the load, we can talk about the generation, we can talk about the force out of the transmission line generation, whatever uncertainty you want to take into account. Those are random variables. We sample from those, we solve the optimization model, we get one sample for the value of the objective function. We keep doing that until we satisfy the requirements of correctly selecting the system. And the parameter of the correct selection, that let's say you want to be guaranteed that 95% of the time, with a confidence of 0.95, that the system that you have selected is the best system. So you keep sampling until you satisfy that probabilistic condition. And you keep solving it, and then the result is going to come out. All right? So the details of this application is in the paper that I mentioned. Now, problem statement number 2, we want to select the best system from K-simulated stochastic system based on a quantile measure. And this is the mathematical definition of a quantile. And basically, if you look at the cumulative distribution, quantile is a point, and we are talking about the value of the Q, the area under the curve, which is about that number. And again, one of our most recent papers, which got accepted into the Informed Journal of Computing, has a mathematical proof for this particular technique, and basically is an asymptotic convergence. The asymptotically proved that the correct selection has been made using quantile as a measure of selection measures. So if you look at the test that we are conducting, again, is a three-way hypothesis test, and we are comparing two systems in pairwise comparisons. And again, we have a continuation region for the quantile, and it has its own mathematics and all this stuff that goes into the parameters that you need to define. And asymptotic validity are on these bases, and again, the proofs are in the appendix of the paper. And the example that I want to show you for this application is the portfolio selection. Let's say that we have 4 different asset classes, and we want to create a portfolio, select the best portfolio from a combination of these 4 asset classes. That's an investment portfolio. And we know that each one of these asset classes, they have certain probability of return. And so one is normal, the other one is normal with different values, log normal, and so forth. And due to the fact that all these four assets are operating in a market environment, they're correlated. And we do have a correlation matrix. So our challenge is to generate correlated random variables based on the correlation that they have, and from these, and evaluate these portfolios, that we have 15 portfolios here, and these 15 portfolios is a different weight on each one of these asset classes. So the first one, for example, is 15% on the asset class number 1, 10% asset class number 2, and so forth. And the last two are bonds, the first one are stocks. All right? So there are different ones, and we have generated 15, a different weight on these, and the question is which one is the best one. So again, we go through the system, and our idea is to generate a quantile, and which is basically the 90% quantile for each one of these distributions, and on that basis we are going to select one. Okay. So now the experiment that we did for this one, and of course the theory that we are using is the difference between two systems on the mean. We have an indifference zone. If it's within that indifference zone, there is no difference between the two systems, and if it's outside, there is. So we can control the indifference zone, and in this case, delta is in indifference zone. So, and these are the probability of correct selection based on our model, and the number of samples that is required, and average number of samples that is required, observation that is required to get to the correct selection. What this shows, as delta increases, that means our indifference zone is bigger, we need less samples. As you want to have a very narrow indifference zone between the systems, we need more samples. Okay, we are going to stay in that continuation zone, and we are going to move forward. So now, let's look at problem number 3. Select the best system from K-simulated stochastic system based on the first order stochastic dominance. Now, in this case, we are going to be using the whole distribution, where mean is just one metric, statistics of that distribution. Mean and variance, we are using 2 statistics of that distribution. And now we are going to use the whole distribution. And so select the best system based on the first order stochastic dominance. And we have a paper in International European Journal of Operational Research, which came out in 2012, and we have one before that, which was in 2010, which added to some of these things. So let me just motivate this idea of the stochastic dominance. Again, more is better. You're going with that. You want to maximize. F1 dominates F2 by first order stochastic dominance if the cumulative distribution of 1 lies below cumulative distribution number 2. So if you look at the figure A, the cumulative distribution of 1 is below cumulative distribution number 2, and so F1 dominates F2. Now, in figure B, they cross. So in that case, they do not dominate each other. Okay? So they do not dominate, and this one dominates. Now, we know that if 2 distributions, 2 systems dominate each other based on the stochastic, first order stochastic dominance, they do dominate each other based on mean. But vice versa is not true. In other words, if you have a mean dominance, not necessarily you're going to have first order stochastic dominance. And in this case, it doesn't have. So our algorithm basically is going to determine whether they're crossing or they're not crossing, because we are looking at the whole domain to compare these things. And we can take a portion of the distribution as well too. If you're only interested in the dominance on the tail of the distribution, you can select a Q set and you just implement the algorithm on the Q set as well. So Again, we are going to go through a series of hypothesis tests, and these are based on quantile. For every quantile, we need to do that. And this particular algorithm was applied to a wireless network, the access point, especially when we are talking about Internet of Things. The access point to the wireless needs to be increased. Rather than going through one point, you need to access the wireless to multiple points. And every device the question is, how are they going to access that the access point? They're going to enter the network. And of course, they can probe it, and signal-to-noise ratio is one of them that can be used, and different algorithms. So my colleagues, they applied this to a wireless network and selecting for devices, selecting the point of access. And their objective was basically throughput. So they want to know, where can I get that it's going to minimize my latency to get in? And especially that becomes important if you're talking about video transmission, because the video packets, they cannot be delayed. You want to get them as soon as possible. So which access point shall I get in there? And they published it, they presented it in this conference. And they showed the results that, which one is better among the network that they had. So the conclusion that I want to leave with you is that the use of risk-sensitive measures for system selection increases the modeling and computational burden. And not always you have to use it, but most of the systems that you're dealing with, especially the ones which are mission critical, we have to take the risk into account. Otherwise, we're going to be in trouble. And the simulated system selection needs to probabilistically guarantee correct selection. And that is something that most engineers ignore. And I think if you rely everything is normal, we can go ahead and simply do that. But if it's not normal, then life is a lot more complicated. And we presented simulated system selection procedure that are sequential, which in a sense minimizes the simulation budget, the number of samples that is needed. And so these are a list of some of our papers that in case the students are interested, they can access them. So I'll be glad to answer any questions that you have.